Beneath the complexities of everyday life, the rules of our universe seem reassuringly simple. This solid bridge supports my weight. The water flowing underneath always goes downhill. And when I throw this stone, it always flies through the air following a predictable path. But as scientists peered deep into the tiny building blocks of matter, all such certainty vanished. They found the weird world of quantum mechanics. Deep down inside everything we see around us, we found a universe completely unlike our own. To paraphrase one of the founders of quantum mechanics, everything we call real is made up of things that cannot be themselves regarded as real. Around 100 years ago, some of the world's greatest scientists began a journey down the rabbit hole into the strange and the bizarre. They found that in the realm of the very small, things could be in two places at once. That their fates are dictated by chance. And that reality itself defies all common sense. And at stake, that everything we thought we knew about the world might turn out to be completely wrong. The story of our descent into scientific madness begins with a most unlikely object. Berlin, 1890. Germany is a new country, recently unified and hungry to industrialize. In this newly unified Germany, a number of new engineering companies were founded. They spent millions buying the European patent for Edison's new invention, the light bulb. The light bulb was the epitome of modern technology, a great optimistic symbol of progress. Engineering companies quickly realized there were fortunes to be made building streetlights for the new German Empire. But what they didn't realize was that they would also unleash a scientific revolution. Strangely enough, this humble object is responsible for the birth of the most important theory in the whole of science, quantum mechanics, a theory that I've spent my life studying. And that's because back in 1900, the light bulb presented a rather strange problem. Engineers knew that if you heated the filament with electricity, it glowed. The physics that underpinned this, though, was completely unknown. But something as basic as the relationship between the temperature of the filament and the color of light it produces was still a complete mystery. A mystery they were obviously keen to solve. And with the help of the new German state, they saw how to steal a march on their competitors. In 1887, the German government invested millions in a new technical research institute here in Berlin, the Physikalisch-Technische Reichsanstalt, or PTR. Then, in 1900, they enlisted a bright, if somewhat straight-laced scientist to help work here. His name was Max Planck. Planck took on a deceptively simple problem: why the color of the light changes as the filament gets hotter. To get a sense of the puzzle facing Planck, I'm going to ride this bicycle with an old-fashioned lamp powered by an old-fashioned dynamo. Obviously, the faster I go, the brighter the light. The more I pedal, the more electricity the dynamo produces, the hotter the filament in the lamp, and the brighter the light. But the light the bulb makes isn't just getting brighter. It's changing color too. As I speed up, the color shifts from red to orange to yellow.
Right, now I'm going to really belt it.
Now the bulb's filament is getting even hotter, but although it certainly gets brighter, the color seems to stay the same, yellow-white. Why doesn't the light get any bluer? To investigate, Planck and his colleagues built this, a black body radiator. It's a special tube they could heat to a very precise temperature and a way to measure the color or frequency of the light it produced. Nowadays, over 100 years later, the PTR still do exactly this kind of measurement, just much more accurately.
The temperature inside here is 841 degrees centigrade. I can feel the heat coming off, and it's glowing with a lovely orangey red color.
It's about the same color as my bike light when I'm cycling slowly. But I want to see something hotter still.
The temperature inside here is about 2,000 degrees centigrade. And it's glowing with a much brighter, whiter colored light. To produce light of this intensity and color requires a power of about 40 kilowatts. Now, that's equivalent to about 400 Ms on a bike cycling very fast, or the combined output of the entire Tour de France.
Although the light is whiter, it's red-white. There's very little blue. Why is blue so much harder to make than red? And further up the spectrum, beyond blue, the so-called ultraviolet is hardly produced at all, even when we look at things as hot as the sun.
Even the sun, at a temperature of 5,500 degrees centigrade, produces mostly white visible light and makes remarkably little ultraviolet light given how hot it is. Why is this? Why is ultraviolet light so hard to make? This remarkable failure of common sense so perplexed scientists of the late 19th century that they gave it a very dramatic name. They called it the ultraviolet catastrophe.
Planck took a crucial first step to solving this. He found the precise mathematical link between the color of light, its frequency, and its energy. But he didn't understand the connection. However, it was another weird anomaly that would really put the cat amongst the pigeons.
In the late 19th century, scientists were studying the then newly discovered radio waves and how they were transmitted. And to do that, they were building experimental rigs very similar to this one. Basically, by spinning this disc, they could generate huge voltages that caused sparks to jump across the gap between the two metal spheres. But in doing so, they discovered something very unexpected to do with light. They found that by shining a powerful light source on the spheres, they could make the sparks jump across more easily. This suggested a mysterious and unexplained connection between light and electricity. To understand what was happening, scientists used this. It's called a gold leaf electroscope. It's basically a more sensitive version of the spark gap apparatus. Now, first of all, I have to charge it up. What I'm doing is adding an excess of electrons that are pushing the two gold leaves apart. Now, first I take red light and shine it on the metal surface, and nothing happens. Even if I increase the brightness of the light, still the gold leaves aren't affected.
Now I'll try this special blue light, rich in ultraviolet.
Immediately, the gold leaves collapse. light can clearly remove static electric charge from the leaves. It can somehow knock out the electrons I added to them. But why is ultraviolet light so much better at doing this than red light? This new puzzle became known as the photoelectric effect. The ultraviolet catastrophe and the photoelectric effect were big problems for physicists, because neither could be understood using the best science of the time. The science that said quite unequivocally that light was a wave. All around us we see light behaving in a perfectly common sense wavy way. Look at the shadow of my hand. It's fuzzy around the edges. We understand this as the light hitting the sides of my hand and bending and smearing out slightly, just like water waves around an obstruction. Perfectly common sense, wave-like behavior. And here's something else, something rather beautiful. Look at these soap bubbles. Shine a light on them and gorgeous colored patterns emerge from nowhere. And this was easily explained if you accept that light was a wave, reflecting off the outer and inner layers of the thin soap film and breaking up into the colors of the rainbow. Rather like ripples on the surface of water, light was simply ripples of energy spreading through space. And this was as firmly accepted as the fact that the Earth was round. But although this wave theory worked perfectly well for shadows and bubbles, when it came to the ultraviolet catastrophe and the photoelectric effect, the wheels started coming off. The problem was this: how could light do this? To truly grasp how absurd this phenomenon was, it might be useful to consider how waves in water behave. This is the wave tank at the RNLI's headquarters in Dorset. It's used to train lifeboat teams to deal with a range of different kinds of water waves. First, small waves, just 30 centimeters high. These waves don't have much energy, hardly enough energy to knock this top can off the other. But when the waves grow to over 1.5 meters, it's a very different proposition. And they're really throwing me about. There's no way I can keep this can balanced on the top. It's clear what water waves are telling us. Bigger, more intense waves have more power. They easily knock me and the cans around. So if light was a wave, more intensity should knock out more electrons. But that's not what happened. Remember, no matter how intense the red light was, it still didn't budge electrons from the metal. But weirdly, weak ultraviolet worked within seconds. So thinking of light as a wave just wasn't adding up. To resolve this, someone needed to think the unthinkable. And in 1905, someone did. You may well have heard of him. His name was Albert Einstein. This is the Archenhold-Sternwarte Observatory in Berlin. Perched on top is a strange, huge iron and steel construction. But it's not a gun. It's actually a telescope. Built in 1896, the telescope was one of the largest of its kind in the world and made the observatory the go-to place to engage and astound the public in new science. Albert Einstein gave a very famous public lecture here on his theory of relativity, which is, of course, what he's most famous for. But it's not the work that won him the Nobel Prize.
In 1905, he'd also come up with a new theory to explain the photoelectric effect. And what he suggested was revolutionary and even heretical.
He argued that we have to forget all about the idea that light is a wave and think of it instead as a stream of tiny bullet-like particles. The term he used to describe a particle of light was a quantum.
To Einstein, a quantum was a tiny lump of energy. And although in 1905 the word wasn't new, the idea that light could be a quantum seemed crazy. And yet, following Einstein's heretical line of thought to its logical conclusion, solved all the problems with light at a single stroke.
I'll try to explain how this helps using a rough analogy. Of course, like all analogies, it's far from perfect, but hopefully it'll give you a sense of the physics to help you understand why thinking of light as a stream of particles solves the mystery of the photoelectric effect. In this analogy, these red balls represent Einstein's light quanta.
And those cans over there are the electricity held in the metal.
Now, in the original experiment, they made electricity flow from the surface of the metal by shining light on it. In my analogy, I'm going to try and knock those tin cans over using these red balls.
Absolutely no effect. That's just like red light. According to Einstein, each particle of red light carries very little energy because red light has a low frequency. So even a very bright red light with many red light particles can't dislodge any electrons from the metal plate, just like the red balls.
Now I'm going to use heavier balls, like these blue golf balls, and I'm going to try and knock off the tin cans with these.
They're like the ultraviolet light in the experiment. Now, each individual light particle carries more energy because ultraviolet light is higher frequency. Just a few of them, like a dim ultraviolet light, are enough to knock the electrons out of the metal plate and collapse the gold leaf.
So Einstein's idea that light is made up of tiny particles or quanta is a wonderful explanation of the photoelectric effect. I remember when I first learnt about this, being blown away by its sheer elegance and simplicity.
But what's more, Einstein's nifty idea also helped solve Planck's mystery of the light bulb. There was more red than ultraviolet because ultraviolet quanta took so much more energy to make, about 100 times more energy. No wonder there are so few of them.
That moment at the beginning of the 20th century signaled a genuine revolution because it demonstrated that the kind of physical science that people were doing right back to Newton and Laplace and people like that, that you needed a completely new approach. Physics has never recovered from that moment in the sense that it's built on that moment. That's where modern physics really began.
But Einstein's theory also left physicists with a dizzying paradox, defying all common sense. Light was definitely a wave, which explained shadows and bubbles. And now it was definitely a particle too, Einstein's quanta, explaining the photoelectric effect and the ultraviolet catastrophe.
Then, just a few years after Einstein's brilliant, crazy idea, the paradox got a lot deeper and a whole lot weirder.
Because what seemed to be a curious mystery about light was about to become a battleground about the nature of reality itself. (1922). The Western world is in the grip of a revolution, a cultural revolution.
James Joyce's Ulysses is published. Stravinsky is at the height of his powers, and Chaplin has just released his first serious movie. The Ottoman Empire collapses. Europe is still recovering from the war to end all wars in which millions of men lost their lives. Russia is newly communist. Meanwhile, America is exporting jazz to the world. Thank you.
In art, politics, literature, economics, there was an insatiable appetite for change. This was the birth of modernism.
You got a heart, but there's no way of knowing. Can see where you are, but can't see where you're going. And I'm stuck here still. I'm tangled up with you. This whole world can be so uncertain.
But, and I might get into trouble for saying this, I would argue that the upheaval that took place in physics at this time would eclipse them all and have far longer lasting consequences. It had begun with the discovery of the weird and contradictory wave-particle nature of light. It ended up as an epic battle fought between the greatest minds in science for the highest possible stakes, the nature of reality itself.
I know I deserve you, I know you're my savior, but when I observe you, you change your behavior so...
On one side, a new wave of modernist revolutionary scientists and their leader, the brilliant Danish physicist Niels Bohr. On the other side, the voice of reason, Albert Einstein, at the height of his powers and now world famous, a formidable adversary.
The battle raged for decades. Actually, in some ways, it still does. It was fought across the world in universities, at conferences, in bars and cafes. It would reduce grown men to tears. And it began with a deceptively simple experiment.
This whole world can be so uncertain.
But weirdly, it was an experiment that wasn't even about light. It was about the particles that make electricity.
In the mid-1920s, an experiment was carried out at Bell Laboratories in New Jersey in America, which uncovered something entirely unexpected about electrons. Now, at the time, it was accepted without question that electrons were these tiny lumps of matter, small but solid particles like miniature billiard balls. In the experiment, they fired a beam of electrons at a crystal and watched how they scattered. Now, that's entirely equivalent to taking a beam of electrons, say from an electron gun, and firing it at a screen with two slits in it, so that the electrons pass through the slits and hit another screen at the back.
What the Bell scientists found shocked the physics world to the core. To understand why, consider a similar experiment with water waves.
I've set up a simple experiment. I have a water ripple tank placed on top of an overhead projector. I have a generator producing waves that pass through two narrow gaps. The projector beams the image of the waves onto the back wall. You can see as the waves come in from the left and squeeze through the two gaps, they spread out on the other side and interfere with each other. What this means is that when you get the crest from one wave meeting the crest from another, they add up to make a higher wave. But when the crest from one meets a trough, they cancel out. This gives rise to these characteristic lines leading to the signature wave pattern. bands of light and dark. Whenever you see these light and dark bands, the signature wave pattern, you know without doubt that you've got wave-like behavior. So, guess what they saw in New Jersey? Now it seemed that firing electrons, tiny solid particles, through the two gaps produced exactly the same kind of pattern, bands of light and dark. First, light, for a long time believed to be a wave, was found to sometimes behave like particles. And now electrons, for a long time believed to be particles, were behaving like waves. But it was actually stranger than that. The wave pattern wasn't merely some result of the entire beam of electrons. More recently, this experiment has been repeated in labs around the world by firing one electron at a time through the slits onto the screen. At first, each electron seems to land randomly on the screen. But gradually a pattern forms. The signature wave pattern. Let me be quite clear about just how weird this is. Remember from the wave tank experiment where the signature wave pattern only exists because each wave passes through both slits and then its two pieces interfere with each other. But here, every individual electron, each single particle, is passing alone through the slits before it hits the screen. And yet, each single electron is still contributing to the signature wave pattern. Each electron has to be behaving like a wave. To explain this strange result, Niels Bohr and his colleagues created quantum mechanics, a crazy theory of light and matter that embraced contradiction and didn't care that it was almost impossible to understand. As Niels Bohr himself said, anyone who isn't shocked by quantum theory hasn't understood it. So, viewers, I'm going to take our tiny electron and use it to delve deep into the heart of reality. And yes, prepare to be shocked, because this is the only way to explain what we observe when a single electron travels through the slits and hits the screen. Quantum mechanics says this: we can't describe what's traveling as a physical object. All we can talk about are the chances of where the electron might be. This wave of chance somehow travels through both slits, producing interference just like the water wave. Then, when it hits the screen, what was just the ghostly possibility of an electron mysteriously becomes real. Let me try and capture just how weird this is with an analogy. If I spin this coin, then all the time it's spinning, it's a blur. I can't tell if it's heads or tails. But if I stop it, I force it to decide, and it's heads. So before, it was sort of not heads or tails, but a mixture of both. But as soon as I've stopped it, I've forced it to make up its mind. This is what Bohr and his supporters claimed was happening with our electrons. In a sense, as it spins, the coin is both heads and tails. Similarly, the electron's wave of chance passes through both slits, two paths at the same time. Our coin then stops at heads. The ethereal wave of probability hits the screen and only then becomes a particle. The quantum world was unlike anything ever seen before. It's hard to overstate just how crazy this is. Bohr was effectively claiming that one can never know where the electron actually is at all until you measure it. And it's not just that you don't know where the electron is. It's weirdly as though the electron itself is everywhere at once. Bear in mind that electrons are among the commonest and most basic building blocks of reality. And yet, here's Bohr saying that only by looking do we actually conjure their position into existence. It's like there's a curtain between us and the quantum world, and behind it, there is no solid reality, just the potential for reality. Things only become real when we pull back the curtain and look. And this view, ladies and gentlemen, became known as the Copenhagen interpretation. Persuasive as it might seem, many people couldn't stomach Niels Bohr's outlandish ideas, and they found a natural leader in the most powerful man in science. Albert Einstein hated this interpretation with every fiber of his being. He famously said, "Does the moon cease to exist when I don't look at it?"
He was very unhappy because it gave limits to knowledge that he didn't think should be final. He thought there should be a better underlying theory.
Over the next 10 years, Einstein and Bohr would argue passionately about whether quantum mechanics meant giving up on reality or not. Then, with two other scientists, Nathan Rosen and Boris Podolsky, Einstein thought they'd found a way to win the argument. He was convinced he'd found a fatal flaw in the Copenhagen interpretation, and its claim that reality was summoned into existence by the act of looking at it. At the heart of Einstein's argument was an aspect of quantum mechanics called entanglement. Now, entanglement is this special, incredibly close relationship between a pair of quantum particles whose fates are intertwined. For example, if they were created in the same event. Let me try and explain this by imagining the two particles are spinning coins. Imagine these coins are two electrons, created from the same event and then moved apart from each other. Quantum mechanics says that because they're created together, they're entangled. And now many of their properties are forever linked, wherever they are. Remember, the Copenhagen interpretation says that until you measure one of the coins, neither of them is heads or tails. In fact, heads and tails don't even exist. And here's where entanglement makes this weird situation even weirder. When we stop the first coin and it becomes heads, because the coins are linked through entanglement, the second coin will simultaneously become tails. And here's the crucial thing. I can't predict what the outcome of my measurement will be, only that they will always be opposite. Einstein seized on this, because it meant that something was happening between the two coins that was almost too crazy to imagine. It's as if the two coins are secretly communicating instantaneously across space and time, even if the first coin was on Earth and the other was on Pluto. Einstein refused to believe this instantaneous, faster-than-light communication. His theory of relativity said that nothing could travel that fast, not even information. So how could one coin instantaneously know how the other would land? He disparagingly called it spooky action at a distance and claimed it was a fatal flaw in the Copenhagen interpretation. What's more, he had a better idea. Einstein believed there was a simpler interpretation, that somehow the destiny of the two coins, whether or not they ended up heads or tails, was already fixed long before we observed them. He said that although it seemed the coin was deciding to be, say, heads at the moment of observation, actually that decision was taken long before. It was just hidden from us. In Einstein's mind, quantum particles were nothing like spinning coins. They were more like, say, a pair of gloves, left and right, separated into boxes. We don't know which box contains which glove until we open one. But when we do, and find, say, a right-handed glove, then immediately we know that the other box contains the left-handed glove. But crucially, this requires no spooky action at a distance. Neither glove has been altered by the act of observation. Both of them were either left or right-handed glove from the beginning, and the only thing that has changed is our knowledge.
So, which is the true description of reality? Bohr's coins, which only become real when we look at them, and then magically communicate to each other? Or Einstein's gloves, which are hidden from us, but are definitely left or right from the beginning?
In other words, is there an objective reality, as Einstein believed, or not, as Bohr maintained? In the late 1930s, as the world plunged into war, there was no way to answer this question. The battle to understand the nature of reality was deadlocked.
The war rolled across Europe, and many of the leading scientists fled to the United States. Then, as the Second World War led inexorably to the Cold War, American science, backed by dollar bills and a new vision of the future, boomed.
Remember, after the war, physicists came back raring to go and try to apply the ideas of quantum theory to atoms, the interaction between electrons and light and what have you. You didn't need to worry about the philosophical side of things to make progress with that. So, as you say, it really took a back seat.
Quantum mechanics led to a profound understanding of semiconductors, which helped create the modern electronic age. It produced lasers, revolutionizing communications, breathtaking new medical advances, and breakthroughs in nuclear power. Quantum mechanics was so successful that most working physicists deliberately chose to ignore Einstein's objections.
It simply didn't matter to them because it worked. They even coined a phrase for it: shut up and calculate.
And the price for this success was that Bohr and Einstein's debate on the reality of the quantum world was simply brushed under the carpet. And amidst all this success and pragmatism, there were few who still worried what it all meant. But as the 50s rolled headlong into the 60s, one lone dissenter worked out how to settle the argument once and for all.
John Bell, I think it's fair to say, isn't well known to the general public. But to physicists like me, he's, well, a hero. He was an original thinker with real courage in his convictions, and the story of his rise to become one of the greats of physics is made even more remarkable when you consider how he started. He was born in Belfast in the 1920s into a poor working-class family. His father was a horse dealer, and they really struggled to get him into Queen's University, Belfast, to study physics. In fact, he was the only one in his family to even finish school. This, I believe, made him insatiably curious, fiery, and stubborn. I remember meeting John Bell in 1989, a year before he died. We were both at a conference in America, and we happened to be sharing a lift just after both attending a talk on quantum mechanics. Keen to say something to the great John Bell, I said I thought the speaker's conclusions were completely crazy. He stared at me with his piercing blue eyes, and for a moment I thought my fledgling physics career was going down the drain. But as the lift doors opened and he was about to leave, he said, "Yes, I completely agree with you. Haven't they heard of the helium problem?" To this day, I'm not quite sure what the helium problem is, but I was just so relieved that John Bell and I agreed. For many years, he worked here at Britain's Atomic Energy Research Centre at Harwell, who built this early experimental nuclear reactor called Dido.
It was here that he started pondering the deep and worrying questions that quantum mechanics raised. Did the quantum world only exist when it was observed? Or was there a deeper truth out there waiting to be discovered? In fact, he was so troubled, he began to wonder if there was a problem at the heart of quantum mechanics.
He famously said, "I hesitate to think it might be wrong, but I know it is rotten." And so in the early 1960s, Bell decided to try and resolve the crisis at the heart of quantum physics. It was an epic challenge.
After all, how do you check if something is real, if something is or isn't there, all without looking? How do you look behind the curtain without pulling it open? But John Bell came up with a brilliant way of doing exactly that.
I think this is one of the most ingenious ideas in the whole of physics. It's certainly one of the most difficult to understand and explain. But I'm going to try and have a go, and yes, I'm afraid I'm going to use another analogy. This time, I'm going to play a game of cards, but it's one for the highest possible stakes, the nature of reality itself.
The card game is against a mysterious quantum dealer. The cards he deals represent any subatomic particles, or even quanta of light, photons. And the game we'll play will ultimately tell us whether Einstein or Bohr was right.
Now, the rules of the game are deceptively simple. The dealer is going to deal 2 cards face down. If they're the same color, I win. If they're different colors, I lose. So, I have a red, so I need another red to win. That's black. I lose. Again, opposite colors. I've lost both those. That's 4 in a row. That's 6 pairs in a row that I've lost. Okay, I think I know what the dealer's doing here. Clearly, the deck has been rigged in advance so that every pair come out as opposite colors.
But there's a simple way to catch the dealer out.
So what we can do now is change the rules of the game. This time, if they are the opposite color, I win.
But once again, every time, my evil quantum opponent beats me.
But again, I can see what the crafty dealer could have done. Maybe while I wasn't looking, he's switched the pack and rigged it so that it always lands in his favor. Now every pair is the same color.
Rigged decks, remember, were what Einstein thought was really happening in the entanglement experiment. He said that just like the gloves were already placed in the box, so the evil dealer stacked the cards before we played. But Niels Bohr's idea was very different. He said red and black don't even exist until you turn them over.
Bell's genius was that he came up with a way of deciding once and for all who was right, Einstein or Bohr. This is how he did it. I'm now not going to tell the dealer which game I want to play, same color wins or different color wins, until after he's dealt the cards. Now, because he can never predict which rules I'm going to play by, he can never stack the deck correctly. Now, he can't win. Or can he? So now the rules are different wins. The same, okay? Same color wins. This gets to the very heart of Bell's idea. If we now start playing and I win as many as I lose, then Einstein was right. The dealer is just a trickster with a gift for sleight of hand. Reality may be tricky, but it does have an objective existence. But what if I lose? Well, then I'm forced to admit that there is no sensible explanation. Each card must be sending secret signals to the other across space and time in defiance of everything we know. I'm forced to accept that at the fundamental quantum level, reality is truly unknowable. Bell reduced this idea into a single mathematical equation that tells us once and for all what seemed unanswerable: how reality really is. John Bell published his idea in 1964, and the extraordinary thing is, at the time, the entire physics community ignored him. Total radio silence. It seems the world simply wasn't ready. Perhaps it was because his equation seemed untestable, or just because nobody thought it was worth investigating. But that was about to change. And the change would come from a very unexpected place.
This is the dawning of the age of Aquarius, age of
America was in crisis over Vietnam, Watergate, feminism, the Black Panthers. And while all this was going on, a small group of hippie physicists were working at the University of Berkeley in California. They did all the hippie things. They smoked dope, they popped LSD, they debated things like Buddhism and telepathy. And they loved quantum mechanics. In its weird version of reality, they saw parallels with their own esoteric beliefs. Their hippie New Age style physics also caught the attention of the public, who read their crazy hippie books that mixed quantum mechanics with Eastern mysticism. Books like The Tao of Physics, The Dancing Wooly Masters, and my personal favorite, Space, Time and Beyond, Towards an Explanation of the Unexplainable. But more importantly for our story, the story of quantum mechanics, these hippie physicists also turned their attention to Einstein's now famous thought experiment and what it told us about the nature of reality. They saw Niels Bohr's secret signaling as proof that physics supported their own ideas. Because if two particles could spookily communicate across space, then ESP, telepathy, and clairvoyance were probably true as well. If only they could prove it really existed. Then, in 1972, they realized that with a bit of mathematical sleight of hand, they could take Bell's equation and experimentally test it. One of their group, John Clauser, borrowed some equipment from the lab he was working in and set up the first genuine and ultimate test of quantum mechanics. This is a picture of that first experiment, built of leftovers and stolen equipment. Over the next few years, it was improved by a team led by Alan Aspect in Paris, making its results more reliable. Over 10 years after Bell first proposed his equation, finally it could be put to the test. This is a modern version of the experiment first carried out by John Clauser and then Alan Aspect. Here, a crystal converts laser light into pairs of entangled light quanta, photons, making two very precise beams. These photons are passed round and bent back again until they pass through these detectors. The two photons are like the two cards the evil dealer places in front of me. We'll measure a property of the photons called polarization, which is equivalent to the color of the playing cards in my game. So, for instance, winning with two matching red cards might be the same as two photons with matching polarization. But because this is quantum mechanics, it's more complicated than my simple card game. And these dials here allow me to measure a second property of the photons as well. Now, that's equivalent to me not only trying to guess the color of the face of the cards, but also trying to guess the color of the back of the cards. Okay, so we're now going to switch on the laser and start the experiment. So this number here gives me the number of photon pairs coming through the experiment. That's equivalent to the pairs of cards in my game. The graph here dropping down gives me the probability that I can win, that I'm guessing right. The more photons, the more accurate it becomes. I'll stop at an uncertainty of about 1%. And the final answer is 0.56. So if I put that into my equation, I now need to run the experiment 3 more times, corresponding to the 4 different settings of these dials. Each run is now like a different set of rules for the quantum dealer. And when I add them up and get the answer, if it's less than 2, then Einstein was right. If it's greater than 2, then Bohr was right. Okay, so now for the second setting. Just remember what the experiment will show. If the numbers come out less than 2, then it's proof the dealer has been stacking the deck. This was Einstein's view. Okay, so the number I get this time is 0.82. Now reset for run 3. But if the result is greater than 2, then the deck cannot be stacked, and something else is at work. Okay, so the run 3 result is minus 0.59. And finally, run 4. This last number will finally reveal if the world follows common sense or something much more bizarre. Okay, so our final result is in, and it's 0.56. So if we turn the laser off... Right, I better just work out the answer. And there we have it, 2.53. It's a number greater than 2. Absolute proof that Albert Einstein was wrong and Niels Bohr was right. The significance of this result is simply enormous. Just remember what it means. Einstein's version of reality cannot be true. No amount of clever jiggery-pokery with our experiment can cheat nature. The two entangled photons' properties couldn't have been set from the beginning, but are summoned into existence only when we measure them. Something strange is linking them across space. Something we can't explain or even imagine other than by using mathematics. And weirder, photons do only become real when we observe them. In some strange sense, it really does suggest the moon doesn't exist when we're not looking. It truly defies common sense. No wonder towards the end of his life, Einstein wrote, "All these 50 years of conscious brooding have brought me no nearer to the question, what are light quanta? Every Tom, Dick and Harry thinks he knows it, but he is mistaken."
The experiment only confirms this. Whatever is happening, we just don't understand it. But it doesn't mean we should stop looking.
While it's true that Einstein's dream of finding a reasonable, common-sense explanation was shattered for good, my own personal view is that this doesn't necessarily banish physical reality.
Like Einstein, I still believe there might be a more palatable explanation underlying the weird results of quantum mechanics. But one thing is clear.
Whether there are physical, spooky connections, whether there are parallel universes, whether we bring reality into existence by looking, whatever the truth is, the weirdness of the quantum world won't go away. It'll rear its ugly head somewhere.
120 years ago, the greatest scientific revolution ever was brought about by a light bulb. And scientists are still using powerful light sources, like X-rays, to unlock nature's mysteries.
This is the Diamond Light Source. It's Britain's single largest science facility. The X-rays produced here are 10 billion times more powerful than the hospital X-ray. With that sort of power, scientists can slice into matter and glimpse those quantum secrets inside.
Researchers here are using this powerful light beam to investigate new materials, which may have the potential to bring about an electronics breakthrough as great as any before. Just as the quantum pioneers of the 20s and 30s ended up bringing about a scientific and technological revolution, so this generation of physicists are set to usher in a new quantum era. An era where Einstein's hated quantum entanglement now produces unbreakable computer security, new kinds of communication systems, super-fast computers, and other advances we can't yet even imagine. And this is why quantum mechanics thrills and frustrates me. It's capricious, it's counterintuitive, it even sometimes feels just plain wrong. And yet, it still surprises us every day.
And I, for one, believe that our knowledge of the quantum world is still far from complete, that there are greater truths about nature yet to be discovered. And that's still what keeps me awake at night.
Next week, join me as my journey into the quantum world gets even more surprising. I investigate how its weird rules are crucial for life, and how the bizarre behavior of subatomic particles might even influence evolution itself.
Coming up next tonight, higher than the tallest building, higher than the biggest plane, higher than everyone, except for 2 actual astronauts. James May goes to the edge of space in just a moment. Then at 10:30, we're off to Hyde Park for some summer sunshine with the Rolling Stones.
I'm